Welcome to the course Formal Language and Automata Theory. In this lecture, again we will continue with context-free grammar concepts. In our earlier lecture, we discussed about introduction to context-free grammar, how to define a context-free grammar, the formal definition, then the production rules of context-free grammar, then examples of context-free grammar. Then we discussed about what is a derivation, how to derive a string from the given context-free grammar, then various types of derivations. We discussed about leftmost derivation and rightmost derivation, then grammar of a language, how to define a grammar of a language, that is L of G, then sentential form, how to define a sentential form and what are the types of sentential forms. Like derivations, there are two types of sentential forms. One is left sentential form and another one is right sentential form. So now we will continue with the remaining topics. So here in this lecture we will discuss about one of the important topic, Parse tree, also called as derivation tree, then applications of context-free grammar. So next class we will discuss another interesting topic related to context-free grammar, ambiguity in grammars and languages, how to define ambiguity, then how to eliminate ambiguity. That we will discuss in next lecture. So now we will come up with the outline of today's lecture. So here first we will discuss about what is a forestry or derivation tree. So then we will demonstrate some examples, construction of a forestry or derivation tree for a given context-free grammar. Then we will see finally what are the applications of context-free grammars. Now coming to our first topic, forestry or derivation tree. So the derivation can be shown in the form of a tree. Such trees are called derivation trees, also called as forest trees. So the derivations can be derived from a given context-free grammar. So the derivation can be shown in the form of hierarchical representation, that is a tree. So such trees are called as derivation tree or forest tree. The leftmost derivation as well as the rightmost derivation can be represented using derivation trees or forest trees. So we can represent both leftmost derivation and rightmost derivations using derivation trees or forest trees. So then how to define derivation tree or forest tree? Formal definition. So like context-free grammar, a derivation tree or forest tree also we shall define formally. So let G equal to VTSP be a context-free grammar or CFG. The tree is a derivation tree or forest tree with the following properties. So here we will take the context-free grammar. From that grammar, we can construct a tree. So when we can say a tree is a derivation tree or how to construct, what are the properties? Here you can see the properties are given below. So any tree in data structures and graphs concepts, we know the concept of tree. What tree contains? It contains a root node, then a set of interior or internal nodes, then finally at bottom it consisting of leaf nodes. So now like as per these three versions, so in the context-free grammar, derivation tree or parse tree, so what is a root, then what is a vertex or interior node or internal node, then what are the leaf nodes, so all will be given below. So the root has a label, yes. So in any derivation tree or parse tree, the root should be labeled by starting variable. So what is S here? S is the start variable, so which can be taken from the variable V from the grammar, that is S belongs to V. So always root has a label S. Then every vertex, that means every node other than root, has a label which is in. So all vertices are labeled with a combination of either variables or terminals or including null. So string of variables or terminals or null or any one individually also, every vertex. Then leaf node. So leaf node means the last node, bottom node. Every leaf node has a label from T, that is terminal, and an internal vertex has a label from V. So now, for example, here you can take any tree which looks like this. So this is called as root. This root is labeled by the start variable. Suppose here you can take some more levels. So now this will call it as vertex. So that is called as internal node. So internal node. So now the bottom we will call it as these are all leaf nodes. So leaf nodes are labeled by terminals, whereas internal nodes are labeled by variables. Then root is labeled by yes, starting variable. So these are all the properties of a derivation tree or forestry. It needs to satisfy always. So now, then if a vertex is labeled with a variable a, and if x1, x2, and so on xn are the children of a from left to right, then a derives x1, x2, x3, and so on xn must be a production in P. Suppose in the derivation tree or parse tree, a node is labeled with A, then it has n children named with x1, x2, and so on xn. So then all these are all connected from left to right. Here you can see this is the node. So here we have the children's x1, x2, and so on xn. So x1, x2, and so on xn are the childrens of A from left to right. So these can be connected to its parent node A from left to right. So when this is possible, so if there is a production, A derives x1, x2, and so on xn. So must be a production in P. So if you have a production like this, you can connect all the childrens which are placed at right hand side to its parent from left to right as shown in this figure. This is another property. Then let us see examples. So let us consider the given context-free grammar. For simple expressions, this example we already discussed in our previous lecture. So a simple expression, context-free grammar, is denoted by G equal to E comma I. These are all the variables, E comma I. Then terminals T. Then starting variable S is E, because the starting variable in this set. Then P are the productions, where terminals are given by the following symbols. So arithmetic operator plus multiplication operator star, then open parenthesis, closure parenthesis, then lowercase letter a and b, then digits 0, 1. These are all the terminals. And P is the set of productions given below. The productions are E derives I, E derives E plus E, E derives E into E, E derives E within parentheses, then I derives A, I derives B, I derives IA, I derives IB, I derives I0, I derives I1. So these are all the productions. So this is one context-free grammar for simple expressions. So now, so whenever if you want to draw a parse tree or derivation tree, first we require derivations. So here we have two types of derivations, what we covered in our earlier lecture. So we have leftmost derivation and rightmost derivation. So you can construct either leftmost derivation or rightmost derivation for any given string, or you can take your own string. So once derivation is done, then we have to draw its derivation tree or parse tree by satisfying the above properties of derivation tree or parse tree. So now here you can see the following figure shows a parse tree or derivation tree which uses the expression grammar for the given derivation. So now here, first we have to consider the derivation shown here. So here the derivation is Here we used C E derives E plus E. First left hand side variable is replaced. Then E is replaced by I. Then leftmost variable I is replaced by A. Now A plus E. Now E is replaced by E into E. Again two variables. So leftmost variable is replaced here by I. Then again I E two variables. Now leftmost variable I is replaced by a terminal B. So now A plus B into now variable only one variable. Now that is replaced by again a variable I. So now I is replaced by a terminal. So finally we got a string A plus B into A. So here each and every step we replaced the leftmost variable, substituted in place of leftmost variable. So therefore this is a leftmost derivation. So whatever the derivation, either leftmost or rightmost derivation, so we can construct its derivation tree or Parse tree. Now this is example of a leftmost derivation. Now we have to construct derivation tree for the final string. The final string, so that can be shown in the form of tree. The tree is called as derivation tree or Parse tree. So how to construct the derivation tree or Parse tree? So in the derivation process, step by step, whatever the substitutions we used, so same thing can be represented in the form of tree. The tree is called as derivation tree or Parse tree. Now step by step, see in the first step what we did. So we have taken the starting variable E. So now this can be labeled as a root node in the derivation tree or Parse tree. Now we can see here E is labeled as a root. So this is root. Here E is so E is start variable. Why? Because the grammar consisting of two variables, that is E and I. Now E is the starting variable. So now root is labeled with starting variable. Now next step what we did, E is replaced by E plus E. So this one. So here we discussed one property. A derives x1, x2, and so on. Xn is a production. Then x1, x2, and so on. Xn are children of A. Those are all connected to A from left to right. In the similar fashion, here E equal to E plus E. Now E plus E are the children of E. Now you can connect E plus E to the root from left to right. Now you can see root is E. So now the expression is E plus E. So left side we have connected the leftmost children E. The next children is plus. Then next children is E. So this is E plus E. So here you will get this is nothing but E plus E. Next another one. Next step what we did, leftmost variable E, that is replaced by I. So here leftmost variable E. So that is replaced by I. So here how this will be done? E derives I. I is the children of E. So only one children. So that is connected to its parent I. So the mean E. Then what we did next step, uh, next E, the rightmost variable E is replaced by E into E. So here this is E replaced by E into E. So this how you got from the production E derives E into E. Next step what we did, the leftmost so before that here what we did, the leftmost variable I is replaced by terminal A. So therefore I is replaced by a terminal A. This can be obtained from the production I derives A. So next what we did, E is replaced by E into E. So here E into E are the children of E. Those are all connected from left to right to its parent. Then what we did, in place of E into E, leftmost E, that is replaced by I. So here, so leftmost E is replaced by I. Then what we did, again the leftmost I is replaced by a terminal B. So here I is replaced by B. So now here the production corresponding production is I derives B. Then what we did, the rightmost variable E is replaced by I. Here the substitution is E derives I. Then last step what we did, the variable I is replaced by a terminal A. So I derives A from the production. So here you can observe. Here in the derivation in bracket, whatever the substitutions we used, so those are all represented in the form of tree in the same order. So this is called as a derivation tree or Parse tree. Here another important point you have to remember. So in the derivation tree or Parse tree, you can see some nodes are represented within circle, then some nodes are not represented within the circle. See how this will be. So here the root and all internal nodes are denoted by within the circle. The root and internal nodes are from variables, variables only. Then all leaf nodes are represented without circle. Then all leaf nodes are terminal symbols only. So here you can observe the leaf nodes. A is one leaf node, small a, plus is one leaf node, then small b is one leaf node, then into is one leaf node, then a is another leaf node. Now you can see, you can connect all the leaf nodes from left to right, excluding null. What you will get here, you can see first a. So first symbol is a. Next one is, next leaf node is plus. Then next leaf node is b. Then next leaf node is star. Next leaf node is a. So you will get our required string, where we got by using a derivation a plus b into a. Same string can be derived by using the derivation tree or parse tree by taking from left to right leaf nodes, excluding null. If any null is there, then you will get your required string. So all leaf nodes must and should be from terminal symbols, whereas root and internal nodes are from variables. See, capital E is a variable. Here also E, I. So see, all variables are used for root and internal nodes representation, whereas leaf nodes are represented by terminal symbols only. So this difference we have to remember while constructing a derivation tree or parse tree. So now see another example. Consider the grammar. So E derives plus EE or into EE or minus EE or X or Y. So E is a grammar. So the question will be given. In examination, you will get questions like this. Find the leftmost and rightmost derivations for the string. So they gave string also and write parse tree. This is one of the previous university examination question. So sometimes they won't give string. At the time, you can take any one string. That string must and should derive from the starting symbol of the given grammar. So for that, you can find its leftmost derivation and rightmost derivation. Then parallel, you have to construct its derivation tree or parse tree associated with its leftmost or rightmost derivations. Now see, let us we will try to derive the given string first using leftmost derivation. So here leftmost derivation, first what we did, so our string must start with plus symbol starting. So compulsory you can take the first production starting with plus only. So that's why we have taken E derives plus EE. This is the only option. So then first symbol is plus. Then what is second symbol in the string? So it start with asterisk, that is multiplication. So again with multiplication, so the leftmost variable E, that should be replaced with the production where it contains multiplication operator at the starting. So for that we have E derives into EE. So that can be substituted into EE. So now plus into two symbols are derived. Next symbol is minus. So now next here we have three variables. So leftmost derivation means each and every step leftmost variable is substituted by using some of the productions in P of the given context free grammar. So now here leftmost E. So next symbol from the string is it start with minus. So minus related production is minus EE. So now plus into minus EE. Now remaining is remains same. So now plus into minus, three symbols are derived. So what is the next symbol? It start with X. So for X and Y terminals directly we have direct values. So that is E derives X and E derives Y. So now we want after minus we want a terminal X. So therefore leftmost E is substituted by X. See here. So then next three variables are there. Again you need to submit I mean substitute leftmost variable only. So after x, what you want next terminal is y. So next e you need to substitute by the terminal y. So e derives y. So then now xy. So after xy again it start with x. Here we have two variables e and e. So leftmost e. So you need to replace it by x. So now e is replaced by x. Then we have only one variable. After x, what we want y. So y is replaced by, I mean e is replaced by y. Now finally you can see the last step of the derivation. So plus into minus xy. This is your required string. So this string is derived by using leftmost derivation. Now same thing you can represent in the form of derivation tree or parse tree. Here you can see same process. First, the first production, what we did, we have taken e as the root, starting variable. So e as the root, then its children are plus ee. You can connect plus ee from left to right. So this part can be constructed using the production e derives plus ee. So plus ee are the children of e. So connected to its root from left to right. So plus ee. So wherever variable is occurred, you can represent within circle. Wherever terminal, you no need to include within the circle. Terminal means further no expansion is possible. That is leaf node. For variable, we have substitutions. So expansion is possible. That too, that expansion depends on the given string, which is going to be derived. So now this is the first step. Second step, what we did, so leftmost e is replaced by into e. So leftmost e means this one is replaced by into ee. So this can be obtained by using the production e derives into ee. Next, what we did, so here in this leftmost e is replaced by minus ee. So this e is replaced by minus ee. For this, the corresponding production is e derives minus ee. Next, what we did, leftmost e, this one is replaced by a terminal x. So this e is replaced by a terminal x. So now for this, the production is e derives x. Then what we did next, leftmost variable is replaced by a terminal y. For this, the corresponding production is e derives y. Then what we did next, leftmost variable that is replaced by x. For this, the corresponding production is e derives x. Then only we have one variable. So at the end, so that is replaced by y. So now e derives y. Its corresponding production is e derives y. Now you can see, take all leaf nodes from left to right, excluding null. Now you can see the first one is here. You can see plus. The second leaf node is what is the second leaf node into. Then third leaf node. So you can give numbering 1, 2, 3, 4, 5, 6, 7. Now you can write in order. So first one is plus, second one is into, third one is minus, fourth one is x, fifth one is y, again sixth one is x, so seventh one is y. Now you can see this is your required string. So which is obtained from the leftmost derivation. Your derivation tree also contains same string, then only the tree is correct. So this is the parse tree for leftmost derivation of the string, the given string. Similarly, same process, so we can do rightmost derivation also. So rightmost derivation, what we have to do, right to left variables needs to be substituted by the corresponding productions from P. So here let us start with E derives plus EE. So now right to left you need to derive the string. So first you need y, then x, then y, then x, then minus, then into, then plus. So right to left, we have to derive the string by substituting the variables from right to left. So now we have plus EE. So rightmost what you want, you want y. So then rightmost E is substituted by y. Therefore, E derives y. E production is used. Now plus EY. So then before y, what you want x. So if you can substitute directly E with x, further we don't have expansion. So we can't get our complete string. That's why in place of E, now we can substitute other productions. So for example, here you can take E derives into EE. Now what will happen? See, plus into EEY. So why? Because into is also required after plus. That's why that multiplication related production also you can substitute. Now here two variables are there. First rightmost E you can replace by xy because already rightmost symbol in the string is y. Then before y you need x. Now E is replaced by x. So now yx, then before x again what you want y. So directly you can't substitute y here. So now the corresponding y productions. So further you want minus symbol. So you can substitute minus related to production. Therefore E derives minus EE. Now you can see here two variables are there. Rightmost E first is replaced. So E is replaced by before x what you want y. So therefore E is replaced by y. So then what you want directly in place of E, again you can see any new production is substituted, directly terminal is required. You can see the string first, it contains plus, then into minus. Then after minus we have x, y, x, y. Already we have y, x, y. Then before y only single terminal is required x. Therefore in place of E, directly you can substitute by x. Then you will get E is replaced by x. Therefore the string is plus into minus x, y, x, y. This is our required string. So this is rightmost derivation. Now you can see its derivation tree or parse tree in the same fashion. First step, what we did, root is labeled with E. Now the children are plus EE are connected from left to right. So plus EE. Wherever terminals directly you can connect, don't include any circle. Wherever variable is there, you can represent within circle. So now for this the production is E derives plus EE. Then what we did, rightmost E substituted by terminal y. So E derives y. That means y is the children of E that is connected to E directly. Only one children. So you can connect anywhere, either left to right, no problem. If more than one children, the order should be maintained from left to right. So then what we did, next rightmost E, this one. So what we did, we substituted this E by x, terminal x. So for this the production is E derives x. Then what we did, next variable E, this is replaced by, so minus EE. Then for this the corresponding production is E derives minus EE. Now for this the corresponding production is here E derives, here what we did, E derives into EE. So now here rightmost variable E replaced by y. So this corresponding production is E derives y. Next only one variable we have E that is replaced by x. So here the corresponding production is E derives x. Now you can take the leaf nodes from left to right excluding null if any null is there. You can first give the numbering. This is 1, this is 2, then this is 3, this is 4, this is 5, this is 6, this is 7. Now you can write in the order the leaf nodes 1, 2, 3, 4, 5, 6, 7. The first one is plus, second one is into, third one is minus, fourth one is x, fifth one is y, sixth one is x, seventh one is y. Now you can see this is our required string. So using rightmost derivation. So this is the derivation or parse tree for the corresponding rightmost derivation. So like that, any given contextual grammar for any string, so we can find the leftmost derivation as well as the rightmost derivation. Then once derivations are obtained, then we can build or construct their corresponding derivation trees or parse trees. So now finally another concept related to derivation tree or parse tree. So the concept is called as yield of a parse tree or derivation tree. So how to define a yield of a derivation tree or parse tree? This is nothing but the yield of tree is the string of symbols obtained only by reading the leaf nodes of the tree from left to right without considering null symbol, that is epsilon or lambda. So this thing we already done. So in our previous example here you can see, so here the yield of the tree is nothing but by reading the leaf nodes from left to right, excluding null. Here you can see this is left to right reading of leaf nodes. The order is 1, 2, 3, 4, 5, 6, 7. Now the values are. So this is nothing but yield of a tree. That means a derivation tree or parse tree. So by reading the string of terminals from the derivation or parse tree from left to right, excluding null, wherever null is there. So that is called as yield of a tree. So now again you can see the yield of a tree is the string of symbols obtained by only reading the leaf nodes. Only leaf nodes you need to read of the tree from left to right without considering the null symbol, that is epsilon or lambda. So the yield of the tree derived always from the root, and the yield of the tree is always terminal string, that is t closure. So compulsory you must derive the yield from the root node. So from the root node, what is the leftmost leaf? So from that you can proceed. So if any null is there, you can exclude. So now the yield of the tree derived always from the root, that is one condition. Then the yield of the tree value is always terminal string, that is t closure. These are all the two conditions. Now in our previous examples, you can take any derivation tree or parse tree. Suppose consider the parse tree given below. Here the yield of this parse tree so is by reading the leaf nodes from left to right. Here you can see this is leaf node 1. First you must start with root. The leftmost leaf is L1. So next leaf is L2. Next leaf is L3. Next leaf is L4. Next leaf is L5. Next leaf is L6. Next leaf is L7. So you can read the string of terminals from the root of the tree from left to right. So now the order is L1, L2, L3, L4, L5, L6, L7. Now you can substitute the values. What is L1 plus? Then what is L2 into? What is L3 minus? What is L4 x? What is L5 y? What is L6 x? What is L7 y? Now you can see. So here nothing but so we have obtained our given string itself. So that is nothing but yield of a derivation tree or parse tree. Therefore, the yield is same, plus into minus xy xy. That is called as yield of a derivation tree or parse tree. Okay, that's all about the concept of derivation tree or parse tree. Now we will move to our next concept, applications of context free grammars. So like every concept, we are discussing about applications like finite automata, regular grammars, then various types of automatons. So the applications we are studying. So here also, what are the applications of context free grammars? So the foremost important application of context free grammars is parser. So parser is also called as syntax analysis, syntax analysis, which is which is a component of a compiler, which is a component of a compiler. So finite automata and regular expressions examples we discussed about the finite automata and regular expressions are used for compiler construction, that is first phase lexical analysis or scanner, whereas syntax analysis also called as parser, that is the second phase of compiler. So for this context free grammars are very much useful. So this is one of the application of context free grammar, so used for representation of parsers or syntax analysis. So before that, see some introduction. Grammars are used to describe programming languages, any grammar. Context-free grammar is used for checking the syntax of programming languages in a compiler. So this is the role of a context-free grammar in syntax analysis or parser. So for checking the syntax of programming languages in compiler. In compiler means in case of parser or syntax analysis, which is the second phase of compiler. And also context-free grammar is a powerful tool used in compiler for syntax analysis, also called as parser, just now we mentioned. The component of compiler, which describes the structure of the source program and represents the structure by a parse tree. So first it takes the structure of the source program of the compiler, then that can be represented in the form of a context-free grammar. Then once context-free grammar is obtained, then you can represent that grammar into a tree form, that is a parse tree or derivation tree. So that is the first application of context-free grammars in parsers. So now another example. So the first example is old one. So there is another new example, that is markup languages. So the development of XML, extensible markup language, so which is a scripting language for designing of web pages or web documents. So the development of XML is widely predicted to facilitate some electronic commerce by allowing participants to share conventions regarding the format of orders, product descriptions, and many other kinds of documents. So, an essential part of XML is document type definition, abbreviated as DTD, which is essentially a context free grammar. So, in XML, DTD is the context free grammar, so which describes the allowable tags and the ways in which these tags may be nested. So in normal HTML, we have hypertext markup language. So here the tags are represented within triangular brackets. Suppose here if you have a paragraph, so here you can write some text. So welcome, then you can end the paragraph. So in HTML language, the tags represents the formatting of text, the style of text. Whereas in XML, so the tags are not for formatting or styling, so which provides semantics. So in XML, tags are used to provide semantics. So one of the example of this XML language, document type definition. This can be defined so doc type, then followed by, here you can represent a list of elements, then you can end this document type. So this is document type definition syntax, DTD, which is essentially a context free grammar. So now elements are list of elements are denoted by using li. So here description of the element, so like that. So for this also context free grammars plays major role. This is the new application of context free grammar. The oldest one is the use of context free grammars in parsers or syntax analysis. So now see the same examples what I explained included here. So tags are the familiar keywords with triangular brackets that we may know from HTML. For example, EM. So this is the starting of EM and end of EM. So what is use of EM? To surround text that needs to be emphasized. So for example here, this is italic. So the text should be in the form of italic format. For that, this EM is used. However, XML tags deal not with formatting of text, just now explained, but with meaning of text. That means provides semantics. So what is semantic? What is semantic? Semantic is nothing but meaningful form. For instance, one could surround a sequence of characters that was intended to be interpreted as a phone number. So this can be provided by using the XML tags, that is a phone, then end of the phone. So which provides the meaning. So like even for address also, you can use like ADDRESS, then end of address ADDRESS. So any tag which provides semantics in XML language, whereas HTML only formatting or styling. Okay, that's all about applications of context free grammars. The first one is parsers, the second one is XML languages. Okay, now we stop here. Then we will review what we discussed in this lecture. First, we discussed about what is a forestry or derivation tree, the formal definition of forestry or derivation tree, then the construction rules of derivation tree or forestry. Then we have demonstrated various examples of a given context-free grammar, finding leftmost derivation and rightmost derivation, then construction of their forestry or derivation trees corresponding to either leftmost or rightmost derivation. Then finally, we discussed about applications of context-free grammar. So the first application is parsers, also called as syntax analysis. Then second application, markup languages, that is XML, markup languages. So next class we will come up with other interesting new topics. So there we will discuss about what is ambiguity. So then what is the role of ambiguity in grammars and languages? Then how to remove ambiguity. So these concepts are also related to context-free grammar. So these topics we will cover in our next lecture.